Okay, welcome to our second lesson on Lenz's Law. Just to remind you that Lenz's Law tells us that if we cause a change in flux in a coil or through a conductor, then the conductor will induce, or the coil will induce, a current, which in turn will create an induced flux, and that induced flux will oppose the change that we've caused. So I'm going to show you now how we can put this to practical use in solving a problem. And in this problem, what we've got is a solenoid, a coil of wire, which is rotating a number of times. And the two ends of this solenoid are connected to an ammeter. Okay, so here's our ammeter here. Oops, no, we want that. And you'll notice that I've drawn in two dots either side of the ammeter. One's marked A, one's marked B. So what we're going to do is this. Here's the problem we want to solve. We've got a magnet that is off here to the right. And there's the north end. And there's the south end of our magnet. So, north and south. And what we're going to do, we're going to move that magnet closer to the coil. So what we're going to do, we're going to grab the magnet and we're going to move it into the coil like that. So we're going to move it from here to here. Okay, so that magnet, is going to move in that direction. And the question we're going to ask is this: as our magnet moves closer to the coil, which direction will a current appear in this coil? This coil is going to induce a current to oppose the change that's being caused by this magnet as it approaches the coil. So as this moves closer, a current's going to be created in the coil. And that current is going to produce its own flux to try to oppose what this magnet is doing. And that current's going to flow in a certain direction in this coil. So the question we wish to ask is, which direction will the current flow in the coil? Will it go through the coil and pass to the ammeter from A to B, or will it flow in the other direction and pass from B to A through the ammeter? So that's the question we're asking. Now, one final little bit of information that's going to help us here, which is something from your Year 11 physics, and that's the idea, and also Year 12, and that's the idea that the change in any quantity, in this case it's the change in flux, is equal to the final flux take away the initial flux, but that can be rewritten more usefully as the final flux plus the negative of the initial flux. Okay? So keep this in mind over the next few minutes as we solve this problem. So here's how we do it. And it's actually not that hard. What we need to do, we need to break down this problem. So we need to work out what the change in flux is occurring and use that to follow this little flow diagram. So in order to work out the change, we need to know what the initial and the final are. So the first thing we do is we try to work out which direction the initial flux is in. And then we need to work out the direction of the final flux. Once we have those two, that will allow us to work out the change in flux. So once we've got those two, we then work out, they'll give us the change in flux. And remember, the change in flux the induced flux, the change in flux that's being caused will induce a flux to oppose it. So the induced flux will be the negative of the change in flux. It's going to oppose it. So it'll be the negative of that. So finally, we will have the induced flux. Okay, so let's proceed. The initial flux. Well, remember, we've got a north-south pole here, so the magnetic field lines are coming out of the north pole and into the south. So which means that the direction of the field as it enters the coil will be to the left. But because the magnet is initially quite a way off, away from the coil, the magnetic field strength will be weak, and therefore the flux will be quite small. So we can represent the flux through the coil initially is going in that direction, but quite a small value. So we'll do a small arrow pointing to the left. As our magnet moves closer to the coil, then more field lines are going to pass through the coil. They're still in the same direction, there's just more of them. So the flux is going to increase. And so we expect the final flux will be large and in that direction. Now, the change in flux, remember the change is the final flux plus the negative of the initial flux. So that means we need to take these vectors and place them head to tail. So the final flux is the purple one. So that's our final flux. So I'll draw that in. There it is. And I need to add the negative of the initial flux. Well, the initial flux is pointing to the left. So the negative of the initial flux, and I'll just draw this in here, the negative of the initial flux will be in that direction. So I need to take my final flux and add the negative of the initial flux, which is this arrow. So I'm going to add it head to tail. There it is. So that means that our change in flux from the tail of the first to the point of the last, our change in flux is in that direction. There it is. There's the change in flux filling up that gap. So that's the change in flux. So the change in flux is pointing to the left. So the change in flux points to the left. That means the induced flux has to oppose that. So how do you oppose the change in flux going to the left? What do you do? What does the coil do? It will produce a flux which points to the right. So the induced flux will point to the right. So how does that then allow us to work out the direction of the current? Well, a week or two ago, we learned something called actually a couple of weeks ago, we learned something called the right-hand grip rule. So we use the right-hand grip rule, but we're going to use it backwards. Because initially, we use the right-hand grip rule to determine the direction of the field if we know the current. Well, this time we know the direction of the field, we want to work out the direction of the current. So what we do is this, and this is probably the part that most people muck up if they're not concentrating. So the direction of the induced flux is to the right because it will oppose the change in flux. So the induced flux is going into the right. So that means the coil wants to induce a flux that passes through the coil in that direction. So what you now need to do is grip any part of this conductor with your right hand using your right hand grip rule. You need to grip any part of this conductor so that your fingers are pointing in the direction of the field of the induced flux. So in other words, if I want to use my right hand, I'm going to I'll stick my fingers in here. So my fingers are going to point in there, and my thumb, if it's my right hand, my thumb is going to be grabbing, like there's my hand there, terrible diagram, but I'm trying to grab the conductor with my right hand so that my fingers curl around and thread into the coil in the same direction as this arrow. And so if you do that, your thumb points in that direction. So just confirm that you get that. Your thumb, if you stick your fingers in the coil in the direction of the induced flux, your thumb, as a result, must point in that direction following the coil. That means that's the direction of our current. So our current is flowing this direction through here from A through to B. So the direction of the current in this coil, in this circuit, will be in that direction. So the current is going around the coil in that direction. That's the direction of the induced current. And we used Lenz's law to work that out. Notice that Lenz's law doesn't give us a value. It doesn't allow us to calculate the size of the current. It just helps us work out the direction of the current if we change the flux. Okay, in our next lesson we will do another example of Lenz's law.